So mixed resistor parts. Most circuits, have both series and parallel components. So to solve these, first of all, you have to be able to identify which ones are in series and which ones are in parallel. If you can't get that far, you're out of luck. Okay? Then simplify the circuit to find the total equivalent resistance, R total. Then we're going to find total current. How? We're going to say, well, total current equals total voltage divided by total resistance. And total voltage, Kelly, is going to be the battery, the chairlift. That's going to be our go-to. And then use Kirchhoff's rules to find the rest. Now, if they tell me total current, I don't walk through all these steps because these steps are to find total current. Or if they give me somewhere with 2, I'm going to tackle it that way first. Example 1 says, identify resistors in series or in parallel. Let's call this R1, R2, and R3. Which resistors are in parallel? R2 and R3. In fact, if I was calculating this, I would say 1 over R parallel is going to be equal to 1 over R2 and 1 over R3. Then I could tell you that the total resistance is going to be R1 plus R parallel. What we're saying here, Harjote, is you can replace these two with one single solitary resistor, and now it's in series with that guy. Add them up. We can get more complicated. What about this middle one here? I think what I would do is I would combine those. Those are in series. I could write that as one resistor. And now, can you see actually it's the same as the question above. The question above has all the current going through R1 and then splitting up into a junction. This has all the current going through R1 and then splitting up through this junction. And I could write this as one single resistor. In other words, now I've turned it into this one, which I would then turn into my simplest form. We can get more complicated than that. If I was solving this, I would write this as a single R parallel. I would write this as a different R parallel. And Kelly, what I would really have now is resistor, a parallel equivalent, a parallel equivalent. Hey, now I got 3 in series. Add them up, and now you have our total. This is going to be our strategy. It's a little easier with numbers. It's considerably easier with numbers. Oh, forgot there was one more. How would I would combine those as one because they're in series with each other. And if I did that, if I imagine that's one single resistor, come on, isn't that exactly the same as this very first diagram? Everybody goes through the first, and we split up. Some go left, some go right. So let's try some. Example 2 says, find all voltages and currents and then draw a summary diagram. Okay. What's the first thing that I would look for? Total current. Did they tell me total current? Rats. Next thing I would look for is any resistor where there's 2 pieces of information. Did they give me another? Rats. So now my third strategy is going to be rewrite this. And what I'm going to do is I'm going to rewrite this as a circuit that looks like this. That's my goal. Where this is R total and this is V total. I'm going to combine it all. That's what I'm saying. So you ready? That's my final goal. So Nate, the first thing that I would do, don't write this down. I'm just going to circle that. Don't circle it because I don't want to muck up my original diagram. I need to combine those two. They are in parallel. So over here in the margin, I'm going to say 1 over R parallel equals 1 over 10 plus 1 over 15. What's the parallel equivalent of this equal to? 6? So Nate, the argument here is 20 volts, 4 ohms, 6 ohms, and we're home. There's our first step. What's the total resistance here, Nate? Nope. 10, okay? Now, it's up to you. Many kids, just by getting to this line, can dispense with drawing this. Many students will say, oh, hey, do it, I got it. Key idea, what you have to be able to realize is that the total resistance is 10 ohms. And I'd put a little box around that. Why is that so handy? Because now, Manisha, I can find total current, which is going to be total voltage divided by total resistance. What's my total voltage in this circuit, folks? 20 volts. What's my total resistance? 10. Hey, Nate, in your head, what's total current? And I'll go to 2 sig figs. I'll go 2.0 amps. I'll draw a little box around that. Remember I said, Jordan, once I have total current, the question falls apart? I'm telling you it will. I'm now going to go skiing on my hill. What's the total current, Nate? Which is leaving the chairlift right here. It's 2 amps. I usually write that in even though there's no blank for it because I just to let myself know, I know how many skiers are on the hill. Let's ski, Peter. Oh. What's the current through this resistor? What must it be? Must be 2 amps. Do I know 2 things? Then I know 4 things. Specifically, I'd like to know the voltage. How many volts do I lose going through that resistor? Okay. And now you could go VI and get the wattage. I'm not going to freak out about that. But for what it's worth, if I know 2, I know 4. Today, I'm just going to focus on V and I and R because I'm going to assume you can go V times I later on when you're done. Okay. How does that help? Well, we could do some kind of figuring out how things split. Wait. How many volts do we lose here? Can I ski this hill and get to the bottom? How high was the chairlift? What's my voltage source? What do I lose here? What must I lose here? Must. In fact, what do I lose in the 15 ohm resistor? Also 12. Do I know 2 in each of those? Hey, I know 4. I'll just find the current. You know what? It's going to be 1.2 amps. And I can do the other one in my head. 0.8. And I could double check by going 12 divided by 15. 0.8 amps. Now, a third trick I could have used if I still needed more information, I could have found the voltage drop in this mythical magic 6 ohm resistor because, oh, what did you say total current was? Total current? 2. And this resistor is? So the voltage in our equivalent has to drop 12. Oh yeah, it did drop 12 in each one. See, that's still, in other words, what we're doing right now, William, is we're proving and reproving in different ways. Kirchhoff's rules and Ohm's law work. And it doesn't really matter what direction you approach it from. One will be a bit more clever and quicker. You can get there. That was so much fun. Let's do another one. Okay. Let's go skiing. Example 3 says, oh, did I find everything I was supposed to find? They wanted, find all voltages and currents, check, check, check. Draw summary diagram, check. Find all voltages and currents, draw summary diagram. Okay. Did they tell me total current anywhere? Nope, but that way's downhill. Suggestions? More specific. Suggestions? No, get the obvious one here. Well, let's do this. Here's the 6 ohm. Here's the 5 ohm. By the way, technically I'm drawing really bad circuits. I should use wavy squiggly lines. I just started a few years ago actually writing the ohms in there, and it stood out more. Kids didn't miss the resistors as much. Also, I have a really tough time doing the resistor symbol as a lefty, especially when it's vertical and it looks ugly, so I'm just going to put the ohmage there. Now, what can I replace that whole thing with? Because those are in series, are they not? Ah. And I'm going to suggest you have now turned it into, well, this question. One resistor, two resistors. So let's tackle it the same way. Let's find the parallel equivalent, which is 1 over R parallel equals 1 over 5 plus 1 over 20. Reciprocal. Oh, 4 ohms. Without me redrawing. Can you tell me what R total is? Aaron? 10, because this is a 4 ohm and it's mathematically in series with that 6. Is that okay, Cliff? Yeah. 10 ohms. And Cliff, while we're on it, what was the total voltage?
30.
So, what's total current? 30 over 10, 3 amps. What else did they want me to find? They said find all voltage drops. Okay. Let's go back to our main diagram, our original circuit. I try and leave the original circuit uncluttered as much as possible. Do I know total current? Yep. So how many amps are leaving the chairlift? What did we say? How many amps are leaving? What did we say?
3 amps.
3 amps? I'll put a little 3 amps right there. Now, let's ski. How many amps are going through this 6 ohm resistor up here on the top? What else do you now know? Voltage? What's the voltage? Technically voltage drop, but how many volts do we lose? 18. How does that help? I know something else now. In the 5 ohm resistor, what must the voltage drop be? Got to be 12 volts. Oh, if I know 2, I know 3 or 4. What's the current in the 12 volt resistor? Sorry, in the 5 ohm resistor. 12 divided by 5, V over R, right? 2.4 amps. So then how many amps went to the right? Must have been, 0.6 amps, 0.6 amps, 0.6 amps. Do I know 2 things in each of those resistors? Well then, hey, I know 3. The first one is going to be I times R, 7.2 volts. The second one, the second 6 ohm resistor, is going to be 3.6 volts. And the third one is going to be 1.2 volts. Also, this here had better add to 12 volts. Otherwise, there's no way that we could split off, go to the right, and meet up. If the guys that went straight downhill went through a 12-volt, steeper, bigger hill, everybody else must have gone through 12 volts of hills if they're able to meet up again. Double check. Does it add to 12? Woohoo! Hey, just for fun, if these are all bulbs, which one is the brightest bulb? Power is how bright an object is. Power is VI. So very quickly go VI, 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 VI. Which one's the brightest bulb in this setup? The 5 ohm one? I don't know. Crunch the numbers is what I'm saying. Someone has a calculator? V equals 1 times R. First one's going to be 108. And then I have, I think it's that one, 7.2 times, there's I times R. Sorry, there's VI. Let's try that again, Mr. Dueck. You're doing this really bad. The top one, the first one, VI, 18 times 3. The first one, this is going to be, let's fill it in just because we're going this far, 54 watts. How about the second one on the top? That's going to be 7.2 times 0.6, V times I. Oh, you know what? This one's not very bright. This is 4.32 watts. Not the brightest bulb in the drawer, so to speak. Not that I'm mentioning any names. The third one is going to be 3.6 times 0.6 times 0.6. This is only 2.16 watts. That's even dimmer. The next one, 2 ohms, is going to be 1.2 times 0.6. This is not even a watt. What about this one in the middle? It's going to be VI. It's going to be 12 times 2.4. 28.8 watts. Hey, which bulb is the brightest? The very first one. Now that I see that, hey, you know what? That makes sense to me because power is what times what? It's V times what? You know what? All the current went through this one. Here the current got split up. I'd be surprised. It's possible. I could probably set up one where one of these guys was brighter than that one, but not likely. What's our strategy? Hey, rewrite it in simplest form as its mathematical equivalent. Face down in block A. Okay. Example 4. What happens to the total current when the switch is closed, as measured by the ammeter? Okay, right now the switch is open. You can see the little switchy thingy. Does it no change, increase, or decrease? And convince me. You know what? Since they gave me numbers in the question, I'm actually just going to crunch this. I'm going to have open and closed. With the switch open, no current can flow this way. This is cut off. In fact, with the switch open, you can just imagine that the circuit looks like those two resistors. Now, if you look at that 20 and that 5, are they parallel or series? With the switch open, they're series, which means what's the total resistance with the switch open? 25. What's the total voltage with the switch open? 100. With the switch open, what's the total current? 4 amps. Now let's try this again with the switch closed. If I get an answer smaller than 4 amps, it decreases. Bigger than 4 amps, increases. No change, no change. Closed. Oh, is our total 20 plus 5 plus 10? No, because now these guys are in parallel. So the first thing I'm going to do when it's closed is go 1 over R parallel, which is 1 over 6 plus 1 over 10. Sorry, 1 over 5 plus 1 over 10. It's going to be 1 over 5 plus 1 over 10. Reciprocal, reciprocal, reciprocal. Do you get 3.33333333? R parallel equals 3.33 ohms. So if you know that the 5 and the 10 can be replaced with 3.33 ohm, can you tell me our total? What's the total resistance of this here circuit here? 23.333333333333. What's the total current when I close the switch? 100 divided by 23.333333. So I'll go plus 20. There's my 23.33. 100 divided by that answer, and I get 4.285. 4.3. What was my current when the switch was open? 4. What's my current when the switch is closed? What's the answer? Does it increase, decrease, or stay the same? It increases. Explain your answer. We just did. We actually solved for each current. Mr. Dueck, could you do this algebraically? Yeah, probably, but I don't know if I'd bother. Not if they give me numbers. Short lesson. Whew. What's your homework? Lots. Here's what I gave my block E's. I think 1, 2, 3, 4, 5, 6, 7, everything but number 9. You normally don't get this much time to work on homework. In fact, you're not going to get the rest of class, but I'm going to give you about a half an hour or so. So use it, please.